The Hyperloop is a proposed mode of passenger and freight transportation that would propel a pod-like vehicle through a reduced pressure tube that could potentially exceed jet speeds. Elon Musk, who first put forward the concept in 2013, described the revolutionary transport as a cross between a Concorde, a railgun, and an air hockey table.
The pods will be propelled either by magnet, a system called passive magnetic levitation, or air expelled from the vessels themselves, and the tubes would be suspended off the ground to protect themselves against weather conditions and earthquakes. Removing almost all friction from the technology means the Hyperloop could reportedly carry passengers at 760 miles per hour within 10 miles per hour of the speed of sound, with unmanned pods being able to go up to 800 miles per hour.
The purpose of this summative is to learn about the Hyperloops, a proposal made by Elon Musk. The reason why we chose the Hyperloop as a topic is because the idea of levitating train really intrigued us and wanted to learn more about the topic.
As a team, we want to further investigate how the Hyperloop levitates, how much more efficient it is compared to a regular train, and how much air resistance and friction as a whole is reduced.
In the Hyperloop, not only will friction be negligible, but if the proposal comes to fruition, the Hyperloop can help use the air, dragging a normal train down, and use that air to make it go faster and help reduce air resistance. The Hyperloop has two key features, helping reduce drag due to air. The first key feature is that the tube tracks will have lower air pressure, and this is helpful because the lower the air pressure, the less drag on the object will have. So this key feature will reduce drag, causing an increase in speed. This is similar to how airplanes go up to high altitudes, since the air pressure is significantly lower.
The second key feature that helps reduce air resistance is the compressor fan located in front of the capsule. The compressor fan is useful since it can redirect air to the back of the capsule or to the air bearings. To add on, air bearings are similar to paddles in which it is located on the sides of the capsule, and their purpose is to use the air gathered from the compressor fan and push it out, helping increase the speed of the capsule and also help in terms of levitation.
A magnetic levitation train uses a linear induction motor. Now this differs from an induction motor in one way. However, to make the difference, we need to observe how an induction motor works. We can observe this by seeing iron ring slices put together along with copper wire threading around each section of the iron ring slice. Now once current is passed through the wires, it will create alternating polarities because of the very nature of how an AC motor works. Now once you have the stator, which is the part that creates the alternating current, you now have a cylinder with electromagnets inside. This cylinder is called the rotor, and because of the alternating currents, it aligns with the current that it's currently channeling, and it starts to spin. This is how we get an induction motor. Now, say for example, if you were to cut apart the induction motor piece by piece and flatten it out. That is the principle of how a magnetic levitation train as well as several other high rail trains work. When you flatten down the two components of the stator and lay them side by side, you can see that when the current is sent in a positive manner this way and a negative manner this way, we will have a magnetic field being created on both ends. The two magnetic fields will collide and create a force sending any projectile that you wish straight along the path. This is how most high rail trains as well as magnetic levitation trains work. By using the base as a projectile, they can launch themselves forward, and by reversing the charge, they can send them backwards along the same track.
At the bottom of the Hyperloop pods, there will be something called a Halbach array, which is a group of permanent magnets that are stuck together in a certain way that maximizes the magnetic field lines. The magnets have their north sides facing different directions and are placed in a certain order so that the field is very strong on one side, weak on the opposite side, and they cancel out on the left and right. Typically, the Halbach array is used to make motors that are in the shape of a circle, which spin on top of a conductive sheet of metal, which will create a repulsion between the conductive sheet and the magnets. This is because the magnetic fields are constantly changing. The current induced by the magnets are not exactly the same as the current on the conductive sheet, which in turn allows it to levitate because it repels off the sheet. How the Hyperloop will move is by having linear motors that will first allow the pods to gain a certain amount of speed and move forward. Just like in the motors, the magnetic fields will be constantly changing now that the pod has started to move, but this time it changes in a straight line rather than in a circle. This will allow the Hyperloop pods to levitate, and the repulsion between the Halbach array and the conductive track will cause the pods to accelerate up to its desired speed, which is said to be 760 miles per hour. In order for the Hyperloop to slow down, the linear motors will create a thrust force the opposite way of the Hyperloop's motion, which will make the pod to go slower because the magnetic fields change less often between the Halbach array and the conductive track until the pod is no longer levitating.
For this experiment, we used the materials of copper wire, a battery, and neodymium magnets in order to simulate the propulsion of the Hyperloop using electromagnetism. To start, we used neodymium magnets instead of normal magnets because neodymium magnets have a strong magnetic force that would make the battery move by itself. To add on, we placed 6 neodymium magnets on both sides of the battery, but specifically, we put the 2 magnets at either end of the battery, in which they're north poles pointing in opposite directions. The reason why the north poles have to be pointed in the opposite direction is because it would create a current in one direction. But if we did not put the like poles in the opposite direction, then both magnets would be pushing or pulling, causing the battery to stay still. After, we used around 8 meters of bare copper wire, not non-bare copper wire because that blocks the current coming from the magnets, which will lead to the battery not moving. And it made a coil that was around 0.264 meters long.
Next, the battery was placed inside the coil. We were able to imitate the propulsion of the maglev and Hyperloop by doing the lab, which involved the use of one battery which had magnets attached to each end and sent into the copper wire as it traveled by itself into the copper wire. This happened when the train is put inside the coils. It caused an electrical current to flow through the wire, which created a magnetic field in the section of wire coils right around the train car. This magnetic field has its own north and south poles which push the train along the track. In order to simulate the air resistance, we taped small pieces of paper onto the coil in such a way that it would make contact with the battery and slow it down in a similar way to how air resistance slows down a train. This makes sense because in both cases, the battery and the actual train in its movement is restricted, which makes it go slower, and this was proven through the experiment because the paper was taped onto the coil. The time it took for the train to pass through increased. By using the formula distance equals velocity divided by time, it is known that if the time increased and the displacement stays the same, the velocity will have to decrease.
To conclude, Hyperloop is the proposal of a levitating train that can be used all across America. The Hyperloop can help increase speed of transportation so anyone can reach multiple distances in a long stretch with hardly any time at all. The Hyperloop has a greater amount of speed than a normal train because it makes friction and air resistance negligible due to its abilities of levitation and air compression.
Through our experiment, we discovered how we can use electromagnetism to simulate the propulsion of the Hyperloop, giving us a better understanding about the proposal and how an object can be affected by outside factors. Currently, the proposal of the Hyperloop is turning into reality, with companies such as Hyperloop One working on the project since 2015. Finally, the Hyperloop is still in the works, but if it comes to fruition, the way people move from one place to another will be changed forever.